Okay, wonderful. Good morning. Hi, I'm Alex Mazursky, and today I'm excited to tell you about our work, ThermalGrasp, enabling thermal feedback even while grasping and walking. This work was done with my lab mates, Jas Brooks and Beza Desta, and advised by Pedro Lopes at the University of Chicago. So here, a user is in VR playing a desert survival game, and to survive, they need to stay warm. So you can see they're holding their hands up to this virtual fire, where importantly, they can physically feel its warmth on their palms. Now, of course, fires can't burn forever without adding wood, so they reach over to grab another log for their fire. Well, they try to grab another log for their fire, but you can see the user is really struggling to pick up this log. Why is this happening? And no, it's not a hand tracking issue. Let's look at some replays from outside VR in order to understand. The tried and true method for thermal feedback has long been Peltier elements, like the ones that she's wearing on her hands that make this virtual fire feel hot. Many years of research have made these the go-to approach. Let's take a look. Peltiers are solid state, meaning they don't involve any giant pumps or messy liquids. And even more importantly, they can do both heating and cooling, unlike other popular approaches like resistive heaters, which only heat. This makes them excellent for wearables like you can see here. However, as you can also see, these devices all significantly cover up the target areas of the skin. And so while these Peltiers make the fire feel very realistic, and even make this firewood prop feel warm since it's close to the fire, they completely block her from being able to grab and manipulate this prop. So while the Peltier is tried and true, it's preventing us from going this next step further for VR realism, overlaying valuable temperature information on top of surfaces and props, like heat on this firewood. And unfortunately, this isn't a trivial problem to solve. The physics of Peltier elements doesn't miniaturize to thinner and smaller form factors that we might see with things like resistive heaters, which again, only do heating and not cooling. And even worse, to do this cooling for more than a few seconds, Peltiers require additional bulky components like heat sinks and fans. And so the problem that we're facing is we're asking users to pick between either thermal realism or physical interaction with props. Our approach aims to address this false dichotomy. Instead, to let the user grasp props like this firewood, along with feel its thermal feedback, we engineered thinner thermal elements that more easily mesh with our hands. And similarly, to let users walk around on different physical surfaces while feeling thermal feedback, we made devices that go on the feet. We call our approach ThermalGrasp. Let me explain how it works. I'll use the hand-worn device as an example. So we move the bulky Peltier element, heatsink, and fan to the back of the hand so that they don't interfere with what we use to feel and manipulate the world. Now the key is that we then attach thermally conductive materials to the Peltiers to conduct the thermal feedback to the palm. And the conductive material that contacts the palm is thin and flexible so as to not interfere with grasping. The benefit of our approach is that it maximizes both thermal realism and physical interaction as shown on these axes. Thermal realism is all about feeling the thermal feedback exactly where you'd expect it. If I step onto something cold, I expect to feel cold on my sole. And that's exactly what you get by attaching the Peltier device directly to the sole. So we can put this direct approach here at great thermal realism since we feel it right at the target, but poor physical interaction because again, this big device is blocking me from feeling the ground. So now let's try moving the Peltier around to boost physical interaction. The extreme case would be this, placing it on the opposite side of the foot. This leaves my sole completely free to feel the grass. So what's the catch? Well, this was actually one of the first things that we tried. In haptics, sometimes you can find unexpected illusions that work just as well as rigorous engineering implementations. Unfortunately for us, this wasn't the case here. Feeling the thermal sensation on top of the foot rather than the sole felt completely unnatural and unexpected. And so this mismatch results in very poor thermal realism. So how can we strike a balance between these two? That's where ThermalGrasp comes in. The feedback is felt directly on the target, giving high thermal realism, and at the same time, users can still walk while wearing these devices and feel textures like grass, or be able to grasp objects. And therefore, we can balance both of our goals. So digging deeper into how we engineered solutions to this challenge, our approach also uses Peltier elements for heating and cooling, but the difference is that we've relocated the bulky components to the backside, but still present the thermal sensation where you'd expect it by using very conductive materials. And so the first conductor that we use is a copper heat pipe. On the outside, this pipe is just a copper tube, but on the inside, it contains water and wicking material. And because of an evaporative process that occurs within the pipes, they have an effective thermal conductivity of about 500 times that of just regular copper. And so these heat pipes are really the key to us being able to transfer heat across these longer distances from the backs of our hands to the front. However, since heat pipes are thick, we then transfer the heat into copper sheet metal, which is much thinner and more flexible at the part that interfaces with the user. And then importantly, we insulate these conductors in foam in order to keep the user from feeling thermal feedback in any undesired location, like the sides. And we only uncover the conductor at the desired location on the skin. Therefore, when we heat a Peltier, heat conducts to the user, and when we cool it, heat conducts away from the user. Now, there's an obvious trade-off of our approach. The rate of temperature change at the skin is proportional to this length of this conductive path. And so this means that our approach, of course, is going to take more time than placing a heater or cooler directly on the skin. And we design our interactive scenarios around this. Please see our paper for an in-depth characterization of this, but you can always increase the power into the Peltier to reduce this latency. The advantage, however, of engaging with this trade-off is that we open up this unique ability to interact with props at the same time as feeling temperature sensations. So for all of this to work, we really need to make sure that our device is so well insulated that it doesn't fall into this trap of being felt at the wrong location. So to find out, we ran user studies. We brought in participants and we put each of these devices on their feet, and we heated and cooled the devices to 40 or 20 degrees Celsius and asked participants to indicate where they felt the sensation by sketching on top of diagrams of the feet. So let's look at the results for directly on the sole. As you'd expect, sensation was mostly felt on the sole. And then similarly, placing the Peltier on the top of the foot gave similar results. Sensation was felt on top of the foot. As you can see, no one felt the temperature on their sole, and that's why earlier I mentioned that this wouldn't feel realistic. Just to be sure and exhaust every option, we also ran pilots in an immersive experience with this device and found that even with suggestive visuals, thermal on the backside was just too great of a mismatch. So finally, here are the results for ThermalGrasp. If it works, then participants will feel the sensations on their sole, and indeed that's the case. And when we compare ThermalGrasp's contours with the direct placement condition, we can see that they look quite similar. ThermalGrasp meets the bar for great thermal realism. So what can we do with both thermal realism and physical interaction? Well, first, we can convince our advisor to fill our lab with a gigantic sandbox. But then we can make a VR desert survival game complete with terrain, props, and thermal feedback. For example, right now she feels like the grass is hot from the desert sun. And now because the sun is setting and the earth is getting colder, she feels the grass beneath her feet cooling. So in order to stay warm through the night, she needs to grow this campfire. And you can see her now searching for wood, walking across the different terrains like sand and grass, all the while feeling this cooling on her hands and feet from the sun having set. And a unique benefit of our approach is that she can even step into this puddle of water while wearing these devices, since the sole has no electronics, it's just sheet metal. And of course, as we know by now, she can pick up this wooden firewood prop because our devices let her grasp. And you can see now she's stepped onto the sand, which is no longer hot from the sun's rays, until she tosses this wood into the fire, and our devices begin heating at maximum power in order to render the surrounding sand on her feet heating up and the embers on her hands. I want to highlight these moments here where she's simultaneously perceiving thermal feedback on top of these physical interactions. Anything she touches can have a thermal layer added to it, and this is uniquely enabled by our wearable approach. Oops. So we ran this, an expanded version of this walkthrough as a study with more events like cold wind, making a torch, and more. And so we brought in these participants and we asked what they thought. For both conditions, the participants rated their sense of realism, immersion, sensory engagement, and enjoyment. And we found that ThermalGrasp provided a more realistic and engaging experience than the baseline. It's likely that ThermalGrasp led to greater realism because it added a sensory modality that aligned with these virtual events. And this speaks to the potential of this approach because the baseline of the experience of VR with props is already very compelling and a large step up from traditional VR. And this is reflected by the baseline achieving high ratings for all these measures as well. At the same time, the limitations of our particular implementation, like slower thermal response times than expected and cumbersome cables, may have limited the immersion and enjoyment of the experience. Still, the majority of participants preferred ThermalGrasp and gave feedback that we further analyze as themes in the paper. For example, some participants were more cautious of the fire's heat and handled the torch with care when they would feel the thermal feedback. So, as I've shown today, we found a way to not only balance thermal realism and physical interaction, but also found that it offered many benefits in VR. These promising first results are a step in the right direction, but we have some ideas to keep improving. For example, to speed up the heat transfer, we could add a second Peltier to sandwich both sides of these heat pipes. And then additionally, advances in materials may lead to even better conformability. We've been conceptualizing with some of these form factors ourselves. So ThermalGrasp fits into a thread of research that our lab has been pursuing recently. How can we make devices that balance virtual and physical realism? The vast majority of haptic devices have been optimizing solely for virtual realism. However, they rarely consider that users also need to feel and manipulate physical interfaces. While today I showed you how this breaks down in the case of passive props in VR, the need for this balance extends far beyond that. As we see augmented reality continue to grow, users will seamlessly and frequently switch between and even mix virtual and physical environments. And so we envision a parallel future for haptic devices that can seamlessly transition between virtual and physical realism. ThermalGrasp is one approach to our vision. I'd like to thank my collaborators on this project and also all of you for your attention, and I'm happy to take any questions.
So thank you for this nice presentation. So we have time for questions.
Bruce Thomas, University of South Australia. Fantastic. I really like this. Could you talk a little bit about the power consumption and the size of the batteries that you had to use for this and the length that they could actually operate for?
Yeah. So we really weren't concerned with power consumption when we designed this. Each of these devices consumes 25 watts. So when you have 4 of them running at a time, you're looking at 100 watts. We had the user, and even were very honest about it in this diagram with the big backpack on. But this was because we didn't really put too much effort into miniaturizing things like the actual power electronics. We had a literal DC power supply plugged into a large laptop battery in the backpack. I still think that would be a bigger issue moving forward, but our focus here was mostly on just seeing what we could do with this approach before providing more optimal efforts. Yep.
And a good approach.
Thank you.
So thank you very much for sharing that really interesting and also really wise approach to different thermal stimuli. So I'm wondering, can you apply your approach even for the situation like we want to present the thermal stimuli to the whole part of the skin, like a whole part of the hand?
Yes. Yeah, that's an excellent question. So this is something that we chose very carefully. So you could see that we had the thermal device coming down to contact the bottom part of the palm rather than the whole hand. And it turns out that this is because our tactile and thermal sensitivity distributions are inverted. So it's obvious that our finger pads are the most sensitive part of the hand to things like touch and pressure. But the opposite is actually true for thermal. So as you can see from these plots here, sort of the bottom part of the hand is more sensitive than the finger pads. And so we're able to kind of balance these two in our particular implementation. That's kind of the goal, is optimizing for both the physical and the virtual coming from the heat. We didn't cover the whole entire hand so that people could still feel the real world. You could try to make these conductors much thinner, and that's something that we're hoping to get to at some point with something like thermal tape or something along those lines, but I don't think it's necessary.
Okay, thank you.
Okay, so let's thank again the